So in the last video, we showed that it does not have a constant variance, which is a problem if we're going to use this for in order to predict. And not having a constant variance, that doesn't necessarily affect the coefficients. However, we have another problem in this. So with ordinary least squares regression, we're regressing log closed price and log square foot. And then we can see that of this, we also have what's called the Durbin-Watson statistic. So this measures autocorrelation. So when this is far from 2, typically the DW statistic is from 0 to 4. If there's the closer it is to 2, the less the lower or the less correlation, lower correlation between the observations or between the residuals. So here we have 0.974. So this is a sign that there is autocorrelation in this model or in this regression. So what autocorrelation means, whenever we say autocorrelation, we're saying typically it's in time series data instead of cross-sectional. But what this means is that our error term is a function of previous error terms. We'll let U be the error term for this. So this means our error term is a function of other error terms. So maybe keep in mind that we're looking at housing prices over a 5-year period. So this perhaps if housing prices are seasonal, maybe seasonality is a problem in this. Maybe seasonality is why we have autocorrelation, or maybe it's something else. But we to measure this, we use the Durbin-Watson statistic. So Durbin-Watson statistic, and it is represented by D. So typically, or always, D is going to be between 0 and 4. If no autocorrelation, meaning that our row up there is equal to 0, then this would mean D would be equal to 2. If there's positive autocorrelation, so positive autocorrelation would mean that maybe when you have positives, you're more likely to have another positive. If you have a negative, you're more likely to have more negatives, meaning which would kind of mean that they come in groups. So you get positives, you're going to have more positives. When you get a negative, you're going to have more negatives. So this is positive autocorrelation is typically the problem. So if our D is less than 2, so if it's between 0 and 2, then you would have positive autocorrelation. So it's positive. Then if it's greater than 2, between 2 and 4, then it's negative. If it's negative, that means that it's always going to be the opposite sign. So it's just going to bounce back and forth. So that's may not be a big problem. Typically, positive autocorrelation is the problem. So this would mean that it comes in groups. So this does affect our coefficients. This affects our estimates in the regression model. So if we go back over here, if we go back to our notebook file, we can look at it. So here we have a Durbin-Watson statistic of 0.974. So this would mean that autocorrelation would probably be present. And then to test for this, there's another tool in the diagnostic package and some of the others, but typically this is a decent amount that we can just show that there is autocorrelation. So just notice it's looking at the wrong one. This is the actual model. This is what we need to be looking at, but still it's 0.913. So autocorrelation is present in this regression model. So this violates the 6 assumptions. So this violates 2 assumptions of the Gauss-Markov assumption. So this is not a good regression to predict housing prices. Maybe the autocorrelation is present because we're treating it as if it's cross-sectional, but maybe the month matters. Maybe housing prices are higher in June. Maybe they're lower in December. Maybe it's just the volume of home sales that affects it. But whatever it is, autocorrelation is present. Maybe it's due to seasonality. Maybe it's due to something else. Maybe it's also because we have we have other data. So the dress shouldn't really matter, but we have city. Maybe if we included city, that would help a little bit. Maybe not. We also have construction. Let's look at construction. If we look at construction, let's do value counts. Value counts. We have, maybe if you broken it up, if you broke it up in brick and block and vinyl and that type of thing, then maybe that would help produce a better model. But for this, just using square footage alone does not produce a good model when predicting the price of a home. So in terms of the project, we've shown that when this is far from 2, it is a sign that error terms are correlated across observations and mean that the regression violates one of the Gauss-Markov assumptions. So we've already shown that. Perhaps this is due to seasonality of housing prices or another underlying cause. However, this ultimately means that the regression model is not reliable for predicting the market price of a home. So for the end of the project, you need to briefly write how this model could potentially be improved and how you would go about improving it. So you could have a dummy variable for construction methods or the exterior of the home. You could have a dummy variable representing the month. Maybe you could break it up by the year or break it up only in months. There's different things that you could do. So go over in detail how you would do that. And this is it for regression analysis.